Good afternoon, everyone. So my name is Gaurav Bafna. I am a senior software engineer at Amazon. With me is Sachin Kale. He's also a senior software engineer at Amazon. Today, we are going to present our journey about how we delivered disaggregated storage in OpenSearch and how we applied the Strangler fig pattern in practice. So let's dive right in. So here is an image of trunk of a tree, and around it there is a mesh of structure. You see is a fig. So the fig germinates in the root of the tree. As it grows, it derives its nutrients from the host tree till it becomes self-sustaining, at which point it decides to strangle the host tree, and what remains is just a reminiscence of the host tree. So you can see that the original host tree has just gone. It has been strangled by the fig. And we'll apply the similar, this gradual practice of process of replacing the host tree is a striking analogy by which we can think of modernizing our legacy software systems. So what are the approaches to software modernization? First of all, we have to understand the trade-offs. As first, one might be tempted to think of the exercise as a simple replacement. We know that what old system does, so just build a new system doing exactly the same thing, but in a new and better technology that is easier to support changes. Replacing a serious system takes a long time, and users can't just wait for the new features, right? So we have to understand the trade-offs of the system so that we can take the right calls at the right time. Identifying the seams. By seams, we mean the existing points, extension points which the system supports. So we can just replace the old system part by part till we are able to gain the confidence that it works exactly the same way, giving the same guarantees, right? The correctness, the durability, the consistency, all of it at the same time. Successfully delivering the parts. As shown in this example, where the tree hasn't gone overnight, right? It has taken over slowly, replacing the older system part by part, allowing things to deliver incrementally, right? By doing things incrementally, we can see how one part is functioning, right? And then we can just change part one by one. So the blast radius of our delivery is contained. So here is the outline of our talk. First, we are going to talk about what disaggregated storage really is, what are the motivation to deliver the same, and the seams, the current extension points we have and how we used it, the challenges, approaches we face in our journey, the key decisions and benefits which we got with implementing this disaggregated storage, the innovations and simplifications we did in the journey, and finally the key takeaways for everyone. So let's start with the OpenSearch cluster architecture. So here the user sends a request to the load balancer, which in turn goes to the data nodes. And there is a cluster manager node which takes care of the metadata of the cluster. It maintains the membership and the shard routing table wherein which shard resides on which data node. And we have an object store on which we take a backup of all the data, and we can restore it at any point of time if we want to. So how does it really work? So users send their data as JSON via REST APIs. It gets stored in the OpenSearch cluster. The data is indexed, making all fields searchable, and then we can retrieve it via the APIs, right? We can use Boolean queries, Boolean expression sorting, analysis, and we can use a dashboard to get the view of all our data at one place, right? So how does the data resides in the OpenSearch cluster? So when a user ingests the document, it gets stored in an index, which is in turn logically divided into shards, multiple shards. So here we are representing the primary shards by green boxes. So primary shards are the one where the request actually lands, and that is driving the indexing into replicas as well. That is the sole authority of the indexing process. And we have replica shards as well to give, it serves two functions. Essentially, one is scalability of your search request and also to give durability. So what is the motivation of during disaggregated storage? First is the slow software patching. So we have all seen how the log4j event affected us, right? We had to patch our OpenSearch clusters, right? With the data movement, it takes a lot amount of time, right? If you do blue-green, you replace the new older nodes with new nodes, the data moves, right? And it takes a lot of time, and many times your node don't have that network bandwidth or CPU to transfer the data. Prolonged downtime during large-scale events. So we have in a cloud world, hardware just can go at any point of time, maybe region-wide or AZ level outages. So we have seen that during outages, there's a loss of data. And to restore the data, we have to use snapshots to go to a point back in time, and then we have to replay the data as well from whatever queue we have purchased the data. So it just increases the overall recovery time of the cluster. Lower cost per GB. Now the data is ever growing, right? So we need to keep delivering the value of OpenSearch. We need to decrease the per GB cost of the cluster. Improve performance for log analytics workloads is on the similar lines. We have to be performant in indexing, in queries, in storage, in all the aspects, right? Minimize deployment intrusive. So as I talked about the rolling, the blue greens, right? We just replace the old nodes by new nodes, so all the data gets copied. So this copying process, it adds the overhead to the older nodes, right? And it affects the indexing rate as well, because it is always also busy in transferring the data to the newer nodes. We don't want that. So we want that to be seamless. There should be no impact to the performance of the cluster. So with this, the storage compute separation, it came in, right? So now this is the current architecture where the data nodes has a local disk attached to it where it stores all the data. Now this is what we are moving towards. So now the compute and storage are completely decoupled. So your data gets stored in the object store. So your compute nodes can scale independently. Also the storage can scale independently. They are not tied to each other, right? So what are the core principles? Open source first. So we want to deliver all the values in open source so that other users of open source can also benefit from it. Vendor neutrality. So we have to support all the vendors. We have to be vendor neutral. So we support S3, Azure, GCP, Oracle. All the object stores are supported with our implementation. Consistency or durability. Consistency or availability. Now this is the principle which has been there in OpenSearch, and we wanted to adhere to the similar principle. We don't want to change that one. Alter semantics only for performance. So there have been some calls we had to take, and we took that very consciously such that it gives us performance benefits. It has to be worth the same. Right? Backward compatibility for seamless transition. Now this ensures that whoever are using the older architecture, if they move to the new, it should be seamless. Their indexing and query should not change during the migration. It should be a seamless behavior. I will hand over to Sachin for taking care of the next part.
Hey, thanks, Gaurav. Hi, everyone. So at this point, we understand why we need storage compute separation in OpenSearch. Now let's take a look at how we build it. Going back to the Strangler fig analogy that we used, a seam represents major building block that we introduce in the system without changing the system that much, right? So what are the different seams that we implemented? The first seam is replication strategy. So earlier, OpenSearch used to have only one replication model, and that is document-based replication. In document-based replication, assume that there are two nodes, one with primary shard, another one is replica shard. So whenever the user request comes, it will go to the primary shard first. Primary will write to its own translog, and then forwards the request to the replica shard. Now, as the document is getting copied here, that's why the name document-based replication. Replica will write to its own translog, will give the ACK back to primary, and primary will give ACK back to user, saying the request is successful. So this is the right request path. Now, a scheduler runs independently on primary shard as well as replica shard and creates segments. And this is how the segments are created. Now, there are two problems with the document-based replication. The first one is segment creation is resource-intensive process. It is CPU-intensive. So if we are creating segments at primary as well as replica, we are doubling the resource consumption. And if the replicas are higher, the CPU consumption is multiplied. The second problem is that the scheduler runs independently on primary and replica. So it is possible that the set of segments that are getting created are different, even though the logical view remains the same, right? Now think about, we want to build a unified storage layer. If there are separate set of segments for the same shard, either we need to persist all the segments copies, which defeats the purpose of the unified storage, or we need to persist only one, but then how do we reconcile if the primary goes down, right? So these are the problems. So to tackle these problems, we introduce a new replication model called as segment-based replication. In segment-based replication, the normal request flow remains same. Primary gets the request, it goes to translog, the translog goes to replica shard as well, and it goes back to the user. What changes here is that segments are now created only at primary. The scheduler runs only at primary and creates the segments, and these segments are then copied to replica. As the segments are getting copied, hence the name segment-based replication. With this, we are solving both the problems that document-based replication had. The first one is that the segment creation is now only at primary, right? So replica is free from segment creation, replica CPU is free, and that can be used for the improved performance. The second problem is that now the same set of the second problem that it is solving is that the same set of segments are present at primary and replica. Now we can have the unified layer which has the set of segment which is same, and then we can copy it effectively, right? So this is how the segment-based replication works, but it also comes with its own set of challenges, right? The first one is refresh lag. Refresh lag refers to the time duration between document getting ingested and it becoming searchable on replica. Now, with document-based replication, the scheduler runs independently on primary and replica, so the time or the refresh lag was mostly bounded by the refresh interval. But that is not the case in the segment-based replication, because those segments, once they are created at primary, they need to be copied over replica. And that depends on multiple things. What is the segment size that is getting copied, how overloaded the primary was at that time, etc. And that can increase the refresh lag for the segment-based replication. The second issue is more prominent with the more number of replicas. So primary is copying the segment to the replica shard. If there is one replica shard, it works fine. If the number of replica grows, the same primary has to copy the same set of segments to all these replicas. So overusing the network bandwidth of the primary. And if the number of replicas keep growing, this can create the oversubscription of the network bandwidth of primary, right? So now let's take a look at how we solve this particular problem with our next sim, and that is remote store integration, right? So before going into the requirements of the remote store, let's understand what are the different data storage components that OpenSearch has. The first one is segment. These are immutable files. The size ranges from few MBs to few GBs. And the second one is translog. These are append-only files where the size ranges from few KBs to few MBs, right? And these are the requirements that we have from the remote store. First of all, it has to have the high availability, at least 4 nines, because most of the applications that we run today, we try to keep the 4 nines of availability. If we choose a remote store which has lower availability, that means our application's availability is bound by that remote store. Of course, it has to have the higher durability than the local disk. Otherwise, what's the point of having the durable store? It should support millions of requests per second. Also, its performance should not degrade with the increased throughput. And in the end, it has to be cost efficient. So when we explored the different types of data stores out there, one type of data store ticked almost all of these boxes, and this is the cloud native blob store. And as Gaurav mentioned earlier, either AWS S3 or Azure blob storage or GCP cloud storage, any one of these can be used for this purpose. So now with remote store integration, this is how the flow works. For the write request, it comes to primary writes to its own translog. But now, when the translog write is successful, primary uploads that translog to the blob store or the remote store. Once remote store says that, okay, this is successful, then it gives back the response back to user saying that my request is successful. And this is how the request flow will work now, right? Going back to the segment creation, segments are created only at primary because this is segment-based replication. And these segments, when they are created, they are uploaded to the remote store, right? And to solve the oversubscription problem, Replica will now start copying these segments from the remote store instead of the primary. And this is how we solve the problem of oversubscription. Sorry. And this is how the remote store integration works, right? One thing to note here is that Replica shard doesn't have translog here. This is because in the happy flow, Replica just needs to serve the search queries using segments. So they really don't need the translog. Replica only needs translog whenever there is the failure scenario where a primary goes down and Replica has to get promoted to the new primary. And this is what we call as failure scenario. So this is what we did as part of this SIEM, right? We used the same interface that we used for the snapshot. If we go to the snapshot interface and see the repository interface that it is using, we reused the same interface so that we didn't have to rewrite the entire thing all over again, going back to the same Strangler fig approach. It offloads the primary storage that earlier was on local disk to the remote store, the configured remote store. And by that, the single source of truth for data now becomes our remote store, not the primary local disk. And as explained earlier, this is built on top of segment replication. Now, what are the different challenges that we faced with this remote store integration, right? And the very first thing that comes to mind is, and this is any distributed system of larger scale can have the same issue whenever there is network partition, and this is multiple writer. So this is our flow, as I explained. User sends the request to primary writes to remote store, and this is how the response goes back. Assume that there is a network partition. Now what happens generally in OpenSearch cluster, whenever there is network partition, cluster manager will understand that the primary is partitioned away, and then it will promote the replica shard to the new primary, right? So this is what it will do. Now the requests are flowing to the new primary shard, and it is now uploading the translog to remote store. But the problem here is that the older primary doesn't know that it is partitioned away. So how do we make sure that it will still not accepting the request and not uploading the data by corrupting the data that is already now overwriting over the other primary? So for that, we introduced something called as consensus-based replication. Earlier what we saw is that whenever the write request comes, primary did not talk to replica at all. But with the consensus-based replication, we added that part where whenever the primary gets the request, before uploading data to remote store, it checks with the replica, hey, am I still primary for you, right? This is called as primary term validation as well. But this is not as expensive as the original replication call. This should be very quick. Just checking that, okay, this is still primary. And with this, now if there is a network partition and the replica becomes the new primary shard, all the requests that are still going to the older primary shard will start failing because it tries to connect to its older replica shard. It asks it whether am I still primary for you, and it either doesn't give response back, or if the network established again, and by that time the replica became new primary, it will say that no, you are not my primary because I became the primary, or some other replica became primary. Right. So the other problem that we faced is the remote store throttling, and this is very prominent in cases where we use the cloud native blob stores, right? And this is something that the snapshot talk also talked about. So I will just skim through it. So what these blob stores do, they have the partitioning based on the prefix or the directory structure, how we store the data. So for example, here base path A, base path B are the two prefixes for object A and B, right? So there would be two partitions that are created, base path A and base path B. But on each partition, there would be some rate limit. So if we go and create one prefix for a cluster, in this case base path cluster M, and all the indexes and shards information is within that cluster, then it can start throttling because there could be a rate limit for that partition. So to tackle it, we identified the high cardinality part of this prefix, which is index ID, shard ID. We moved it to upfront to the prefix and created a hash, so that now across multiple clusters, we can have a certain global set of partitions created, and that can be shared with these all the shards. So this is how we solve the remote store throttling problem. Also, we saw that whenever the request comes, the primary goes and uploads the translog. But if we do that, it will end up uploading so many small translog files that it can make it infeasible. So what we did is that we introduced the concept of buffer interval. So each write request, whenever it comes, it will wait at most for 650 milliseconds. And then all the translog writes that happen during that 650 milliseconds, it collects it, creates one translog file, and then uploads. But due to that, we can see the at most 650 millisecond latency increase for the bulk calls, right? But that does not necessarily mean that the throughput is also decreased, because your replica is now having more CPU available. So you can increase the number of clients to get the maximum throughput. And the throughput will definitely be higher than earlier. Also, whenever the failure happens now, as we saw, translog needs to be getting downloaded on the replica, so the failover recovery time would be higher than the document-based replication. And as we are dealing with the remote store now, we have to be extra cautious when we do the data integrity checks. Whenever we are uploading as well as downloading file from the remote store, we need to make sure that we are having the stringent data integrity checks. Right. Now, with our first two themes, we are able to achieve the storage and compute separation that we wanted. And any new cluster now will be able to achieve that part, right? But what happens to the existing clusters, right? Existing clusters are running on document-based replication. How do we move them from one to another? And this is where our third theme comes into picture: migration of existing clusters to segment replication and remote back storage. And so what happens, right? OpenSearch users run business critical applications with OpenSearch, right? So it is not feasible for them to stop the traffic completely, do the migration, and then resume the traffic. Rather, the expectation is we should be able to migrate the cluster while serving the live traffic without impacting any performance, right? So it should be similar to changing the parts of the live vehicle, right, running vehicle. So basically, we want to move from a cluster which is using document-based replication and is not using remote store to a state where it uses both. And these are the challenges in the migration, right? The first one is definitely live migration. The second one is, now if I have the huge cluster with some TBs of data, in order to make it the remote back storage cluster, I need to make sure that the entire data is uploaded, right? If I create a new cluster, whenever the data is getting indexed, it is getting uploaded. But in the case of migration, whatever data that was already there has to be uploaded, and that data can be huge. So that syncing data also can be a concern here. And again, going back to the volume of data, if I have the cluster which has 500 TB of data, I started migration, 490 TB is completed, and then migration failed due to any reason. There is a AZ outage, for example. Now, whenever things go back to normal, I should be able to resume the migration. I should not be able to re-upload the entire 490 TB of data, otherwise I will just go into the loop. And I should be having some mechanism to understand that my migration has failed, and then I should be able to auto-recover from it. So this is what we did when we introduced the migration support in OpenSearch, and this is how we will be able to achieve that. Assume that, again, the two nodes, one is primary, one is replica, and this is document replication. So in order to migrate this cluster to segment replication and document the remote back storage, we introduced 2 nodes. This is on the version which understands segment replication and remote back storage. This was on the older version. We introduced 2 nodes, and now we started migrating the primary shard, right? While migrating the primary shards, we copied the segments from the older primary shard to the newer primary shard, and then at the same time we started uploading the segments to the remote store. Once the segment upload completes, we start migrating copying the translog as well, translog operations. And once the new primary shard is up to date with the older primary shard, we atomically shift it. And this is how the primary shard is shifted. One thing here is the new primary shard is still replicating data to the older replica shard using document-based replication. Now this is important. We won't be able to atomically shift all the shards at the same time. So we have to go one by one. So the new primary shard understands dual replication, which means it knows how to replicate data to the new replica using segment replication, and how to replicate data to old replica using document replication. And similarly now, as the primary is ready, the replica now starts downloading segments from remote store, and once it is ready, the older replica is also automatically shifted to the new replica. And this is how the migration is achieved. And now we have only and then we discard the older nodes. Yeah, these are the seams that we went through. I think we have one more seam to go through, but yeah, I don't think we have enough time for that. I'll just go a few of the things, and some of the things are already covered in the snapshot task. For example, how do we go the data integrity check? As we are uploading some metadata file as well, how do we make them backward compatible using versioning? How do we name metadata files so that the list API for the blob store will always give me the latest file at the top? What should be our consistency model, and how do we make sure that the same immutability guarantee that Lucene has, our other metadata files also preserve the same? What are the file content required? For example, what are the content bytes, codec, content length, or checksum that is required for the integrity check is something that we covered in the file formats. The file name format is something that I was talking about. If we have the 2 files, if we take the S3 example here, right, it will always list in the lexicographic order. So what we did is that we changed the name or the identifier with the inverted value, which is long max minus value, and we padded it leading 0 so that we will always get the latest file at the top. Yeah, this is from my side. For the next section, I'm heading back to Gaurav.
Hey, thanks, Sachin. So let's go over the key decisions that we took during this journey. First is throughput over latency. As Sachin explained, that we buffer the request before uploading it to remote store, right? So the latency will increase. But what about the throughput? Meanwhile, the one thread is waiting to upload to the remote store. Your other threads are empty. They are doing nothing. So what we can do is we can have more connections on the client side to send more data, so that the overall throughput is much higher. Why? Because we have more CPUs. Replica is no more doing any indexing, right? So we have more CPUs, so we can do more indexing. The only cost is at the client side, where they have to increase the number of connections. Mixed mode support. So we intentionally reduce the number of modes we would support. For example, if a cluster is remote store backed, we ensured that all the indices are remote store backed and no index is document replication based, because we want to give the durability guarantees on a cluster level, not on index level. It also reduces the number of modes and the confusion while operating these clusters. Durability over availability. So we would prefer to be guarantees of remote store durability, right? So over availability guarantees. Read after write consistency. So now as Sachin talked about the refresh lag, right? So the replica is falling behind. It needs to download some segments, and it might take some extra amount of time. And some users might need read after write consistency. So we introduced reading only from primary node, so that they could get this read after write consistency. Though it would not scale, but it would still serve their purpose. Data corruption risks. So we were in document replication, you send over the whole document over to the replica, and it also does the indexing, but here replica is not doing any indexing. So any corruption, let's say CPU corruption in your primary, it can lead to corruption of data, and if it gets uploaded to the remote store, your data is gone. You have no way of recovering your data. So what we are doing is, before uploading to remote store, we are doing an end-to-end integrity check, and if it fails, we just fail the primary, we just fail the request as well, so that when the new primary comes up, the request is going to be retried from the client side, but your data has not been corrupted. So at the cost of availability, we have ensured that the data remains durable. Some of the innovations and simplifications which we got was on snapshot. This was covered in other talks, so I'm just going to give an overview. So this is reusing the data which we have in the remote store to restore the data. So the snapshots become very lightweight. You don't need to upload any data. You just download it from the remote store as needed. So the create snapshot becomes very lightweight, and the restore just uses the remote segment store. So some of the simplifications which are going to come as a follow-up is point-in-time restore, wherein you could just specify a time and we would go back to that version. So snapshots are point in time, but with this point in time, you can go back to any point of time, right? Intelligent data tiering is what is going to come, in which the data is going to be tiered to remote store completely. It will not be downloaded to the local disk as done today. Read-write separation is also one use case which is going in 3.0. So the readers will independently get the data from the remote store. It would no longer need to communicate to the writers, right? So they can scale independently. So it is based out of remote store. Cross-test replication, today it uses document-based replication, but we have an item in which the cross-test replication will also be used based upon the object store. So again, no duplicate indexing here. So even multi-region active we could just deliver with this object store. So what are the key takeaways? Define your tenets. So our tenets help in making our key decisions. Let's say durability over availability, throughput over latency, right? So if we define our tenets earlier on, it helps in the making decision easily. Don't try building an ideal system, because we can't really do that, right? We have to make some trade-offs always, right? Don't reinvent the wheel. So what we did with object store and all of the seams, right? We reuse the existing interfaces. Even in migration, we just use the existing recovery process, and we just created our own seeding process in the same recovery logic. We didn't have to rewrite it from the scratch. High judgment calls matters, and definitely inventing to simplify the things so that we can deliver value to our users. So yeah, this is all we had. I would like to take some questions now if we have.
Hey, hi. So in this case, how do you deal with the increase in cost that comes from the increase in upload and download from an external remote storage? Because if you move to an S3 or a GCS bucket, you're now paying for every egress and ingress that happens. So how does that fit into certain type of workloads?
Yeah, good question. So with the translog upload, we have introduced some buffering. So the default is 650 millisecond, but you can tune it as per your need. So if there is a cost concern, you can increase it, right? So yeah, so that is one way, and we are also working on further decreasing it. So today the segment uploads are tied to refresh. So we are working on an item where the uploads to remote store will become decoupled. So it will be uploaded only if you have sufficient amount of data, let's say 100 MB or let's say 10-second or whatever, right? So we are working on further reducing the calls to remote store. So that when you have sizable data, then only you upload to remote store. Meanwhile, the replica can just fetch from the primary during that time. So yeah, we
got it. Thank you. Second question. So how do you deal with replicas being too far behind than the rest of the replicas? Because if you have 10 segments that are available from a primary's perspective, one of the replicas can only download 2 segments versus another replica that may have downloaded 7 segments, right? So based on which replica your call goes to, your consistency is different. So do you have some sort of a monitoring in place that tells you whether a replica is too far behind and maybe you need to do some actions? How does that work?
Sachin, you want to take that?
Yeah, that is a good question, right? And that goes back to the challenge that we faced with the refresh lag.
Your mic is off.
Sorry. With the refresh lag. So it is possible that with remote store, the refresh lag, or we generally call it as data freshness lag, will increase. So we have certain mechanisms, kind of back pressure that we have built in. If the refresh lag increases a lot between primary and replica, we stop the writes. Right. This is tunable though. It's up to the user what value of the refresh lag they are comfortable with, and then they can tune that. The second thing that and there is RFC we have opened for the same as well, that there are multiple things that we are trying out to overall reduce this particular refresh lag. Right. One of the examples that I can give is that whenever the segments are merged, right, the merged segment generally is bigger in size, but that actually does not participate or it does not contribute anything new to the replica's document visibility. So in that case, can we give the low priority to this merge segment and prioritize the refresh segment replication, right? So these are some of the things that are still in progress, but yeah, we definitely have the monitoring and the back.
Got it. Thank you.
So when you discussed about that problem number 2, where like so you will copy the segments so where the network lag can be increased. So that is the problem you are solving with the remote storage, correct? So if we don't have a solution of remote storage and then we have to stay with the same data nodes, so the segment replication still is a recommended approach, or you don't recommend?
It would be. It depends on. So I think you are mentioning the oversubscription of network bandwidth of primary.
Yes. Yes.
Right. So that problem generally occurs if you have large number of replicas, right? And that also happen if the primary are not equally distributed. Let's say you have one primary and that one node that has most of the primaries, and now that node is responsible for replicating the segments of each of these shards to all the replicas. In that case, it can happen, right? The oversubscription of network bandwidth with the segment replication as well. If your number of replicas are less, then this problem should not occur, but you should still keep an eye on having the uniform distribution of primary shards.
So that will be automatically taken care by the thing, right? We don't, as an...
It should be, yeah. We have the allocation and relocation policies in place, which should do it automatically, but in certain times it is possible that the primaries are still skewed. For example, if you have 3 nodes and your number of primaries are 4, so there will be one node with 2 primaries anyway, right? So we have to have the number of primaries defined in the multiple of the number of data nodes. So these things will also help.
Okay, thank you. So another question which you said, right, the consequences, you solved that when you say I am not primary and you are primary. So if that guy replies saying that, okay, I am your primary, and then at that time the network is lost, what will happen?
Okay, so you are saying that the primary gives the response, asks the replica saying that am I still the primary for you?
And then that guy lost.
Yeah. Then in that case, the primary doesn't get the ACK back from the replica. It rejects the request.
Okay.
Because it is possible that either it is a temporary issue or this is not actually the primary. So we definitely value the durability of the data more. We don't want to say that the request is successful, but afterwards it is lost. So we fail the request, so user can retry the request in that
Okay,
case.
okay, that makes sense. Thank you.
Hi. So when you say the failover scenarios, because the translogs, on case of the failover, you are copying that translog, right? If the translogs are copied and during that time the first node came up, the translogs is still copied over there on the replica, or you are again in next failover you are again making copy of the same? And I mean related to that, the translog would be copied to all the replicas, or it would be copied to only the replica which is going to be primary at this time?
Yeah, so once the cluster manager decides that, hey, that primary has gone down, it will change a replica and it will make it a primary. So only that replica copy, which is now primary, will download the translog and it will start taking in writes. So other replicas would remain replica, they won't do anything. So even if that other primary comes up, it will only become a replica copy. It would not become primary again. So that's how the semantics there.
So it will increase a bit time for failover request, because it will take some time to put all the translog on the next primary, right?
It will need to do the translog download, but as per the translogs are not huge. Is that what we have observed? And we have observed that only some seconds are added to the overall recovery time. So in less than single percentage is of overall time is what the impact is. It's not that significant.
Thank you.
Time is up.
My question is slightly more operational, I guess, because a lot of people have talked about the depth of what happens inside. Here we're trading off compute for I/O in a nutshell, right? So are there any operational recommendations where you would say that your shard sizes shouldn't go beyond this now, or your segment sizes, your merge policies should look different, or something of that sort? Are there any insights that you have from here?
Yeah, so operational side, the shard size or the number of shards, those recommendations generally remain same as they were in, let's say, document-based replication. One thing we definitely recommend, and that comes with the segment-based replication, not just remote store, and with both as well, is that, as I was saying, is that the primaries need to be distributed equally. So let's say assume that 2 nodes, there are 2 primary, 2 replicas. In document-based replication, it doesn't matter because all the 4 shards are creating the segments. So they are using CPU equally. In segment-based replication, if my one node has both the primaries and one node has both the replicas, there could be a CPU skew, where the first node, which has 2 primaries, the CPU utilization would be spiking up. That's why we have to keep an eye on whether my primaries are distributed equally.
Doesn't OpenSearch already, the AWS managed versions, for instance, automatically manage this?
It tries to do that. There are certain constructs in OpenSearch that tries to balance the primaries as well. We have added it as part of the remote store, but it may not constrain it. And for that, we have added a new change where there is an index level setting which says what are the total primary shards per node I have to keep. And that will give the constraint. But before 3.0, there wasn't any constraint that will tell that on a node there should be at least these many primary for an index.
Got it. Thank you.
Thanks, folks.
Thanks, everyone.